Okay, section 3.6, we talk about, still talking about first order kinetics, and now we're tying it to the concept of half-life. So half-life is the amount of time required for the concentration of a reactant to decrease to half of its initial concentration. So if we start with the concentration of a reactant that is 1.0 molar, then the half-life is the amount of time it takes to get down to 0.5 molar. Okay. So here's the equation for half-life. So the symbol for half-life is T to the 1/2. And at the half-life, the concentration at half-life is equal to just simply 1/2 of the initial concentration. Okay. So if we remember the integrated rate law for the first order reaction, this is it. It's the log of the concentration A over the log of the initial concentration equals minus kT. If we say that we're looking for the time it takes to get to 1/2 of the concentration, well then we can replace A at time t with 1/2 of the initial concentration. If we do that, what happens is we can then cancel A naught, and we end up with the log of 1/2 equals minus kT to the 1/2. And the log of 1/2 is minus 0.693. So we can rearrange this equation now, and this is what we get. This is the half-life equation for a first order reaction. Only works for a first order. It's a very simple equation. It's on the equation sheet. And the really interesting thing is it doesn't matter how much A we start with, what the concentration of A is. The concentration of A shows up nowhere in this equation. Okay, so let's take a look. So from a particulate standpoint, this is how half-life works. So for a given amount of time, let's say in this first reaction vessel we have 16 units of something. Maybe they're moles or maybe they're just individual molecules. And after the same size time interval, I am now down to half as many molecules, down to 8. Another same time interval and I'm down to 4. Another same time interval and I am down to 2. And as you can imagine, if I go down to time 5, I'm going to be down to 1. Alright, so some of the questions that you get asked on the AP test are pretty simple if you think about what we just looked at. And you don't have to even do any calculation. So if a first order reaction started with 8 molar of a substance and the half-life was 1 minute, what concentration would remain after 3 minutes? So let's think about this. So I have 8 molar, and if I go down 1 half-life, 1 minute, I should have 4 molar. 1 more minute, this is at 2 minutes total, I should be at 2 molar. At 3 minutes total, I am at 1 molar. So my answer is going to be 1 molar. Alright, so here's another problem. A first order reaction has a rate constant of 3 times 10 to the minus third. What time is required for the reaction to be 75% complete? Okay, so if you think about this, if I have, let's say I have some concentration X, after 1 half-life, I'm going to have 0.5 X left, right? And after another half-life, I'm going to have 0.25 of X left over. So I'm going to, basically, to be 75% complete, I'm going to have 25% left. So this question is really asking what is the time for 2 half-lives. Okay, so let's go ahead and try to solve this. So we can use that simple equation, T 1/2 equals 0.693 over 3 times 10 to the minus third seconds to the minus 1. If I divide these numbers, I get 231. Now, if I have 1 over s to the minus 1, that is the same thing, if I invert this, as s, right? So that's seconds. I really only know this to 2 sig figs based on my given here, so that's 230 seconds is my half-life. But I want to know 2 half-lives, so 2 time and a half is going to be 2 times 230 seconds, or 460 seconds. Alright, so here's another equation. First order reaction has a rate constant, same rate constant as we just looked at. The time required for the reaction to be 30% complete is what? Now, this is not as simple as a certain number of even multiples of half-lives. So we can't use the method we used in the previous problem, but we could use the integrated rate law. And if we do that, so here's some reason, some pretty good reason for you to remember this law, because it's not on the equation sheet as such. X minus kt. Okay, and if I do that, alright, so if my reaction is 30% complete, what does that mean in terms of what I have left? If I'm 30% complete, I should have 70% left, right? So I could say the log of 0.7 times the initial concentration of A naught over concentration of A naught is equal to minus KT. And if I do that, now my A naughts cancel out, and I get the log of 0.7 equals minus KT. So T is going to be the log of 0.7, which is 0.357, negative 0.357. I put that over my K, right? Divide by K, and that's going to be 3 times 10 to the minus 3 seconds to the minus 1. And this is also a negative value, right? Because it's, when I rearrange this equation, I end up with T is equal to log of 7 over minus K, right? So that, when I plug it into my calculator, I get 119, and that would be seconds, right? Seconds to the minus 1 down here. I only have 2 sig figs, so it's 120 seconds. And that would be my answer. Okay.